I hope that you enjoyed the C60 at 40 for the last 2 days. It was really awesome. And since we all learned a lot about carbon and its various polymorphs, I'm going to carry on that theme a little bit today by telling you about polymorphs, but more specifically about polytypes. And that is going to be behind the story that I want to tell you today about the rich physics of transition metal dichalcogenides. How many of you know what chalcogenides are, or transition metal dichalcogenides are? No? All right, then I'm going to, come on, raise your hand if you do know what transition metal dichalcogenides are. Okay, so there are some people that know. All right, good. For those of you that don't, you're in the right place. I'm going to tell you, and I hope to tell you also why you should care about them, okay? So, if nothing else, what you should get from today is a lot of what's on this slide. The fact that this is a class of materials that has a very versatile crystal structure, and that's reflected in the very diverse and rich physics and physical properties. And from there, it's only one more step towards them lending themselves very well to emergent properties and also applications. So this is a lot of the work that's being done in my lab. I do a lot more than just transition metal dichalcogenides. For those of you that may not know me, I'm Emilia Morosan, and I'm a professor of physics and astronomy. But I also have appointments in different departments. As you all know, the boundaries here at Rice are very fuzzy, and that's a good thing because that's how we can have all of this diverse community. This is a snapshot, or some snapshots of what my students do in my lab. A lot of what we do has to do with synthesis, discovery of new materials, and characterization. So some or a lot of you may be more engineering minded, some of you may be chemistry minded, some of you may be physics minded. We try to use all of those tools in the research that we do. So a lot of what I'm going to tell you today will be relevant, and I hope that you're going to learn some of the rich physics of dichalcogenides. So this is a broad outline of what I want to tell you. A lot of times when I give these talks to people who may not be familiar with the work that I do, it's useful to talk about single crystals. Why should you care about single crystals, and what are they? And then naturally we have to talk about the difference between single crystals versus polycrystals. So I'll tell you a little bit about that. And then I'll talk about the transition metal dichalcogenides. I'm going to be referring to them as TMDs. And I'll delve into the rich physics with some examples. All right, so let's start with what TMDs are. They're materials or compounds that are formed with a transition metal, as the name suggests, and a chalcogen. And for those of you that don't know what chalcogens are, they're the sulfur, selenium, tellurium, this column here in the periodic table. And a lot of the chalcogenides, and the dichalcogenides in particular, have this formula TX2. And they're formed with these transition metals and with the dichalcogenides, like I said. They have very diverse properties, even in this TX2 form. They can be metals, insulators, semi-metals, semiconductors, superconductors. And then we can do something else with them when we can even expand their structural and physical properties even more. Because of their layered nature, as I'm going to show you in a second, we can actually insert atoms in different spots in that crystal structure, and depending on the choice of atom, we can impart them with magnetism or topological properties, etc. So I'll come back to this, but this is a snapshot of the different polytypes that the TMDs can form in, and the little names that you see underneath here are the different compounds that form in that particular polytype. So you can notice one of two things immediately, that many compounds form in any one polytype, and if you really paid attention, although I can't expect that you can all read all that small text, if you looked carefully, you would see that there are compounds that form in almost all of the polytypes. So tantalum disulfide, for example, is one compound which will form in almost all of these polytypes. So before I speak of polytypes anymore without some of you knowing what they are, let me just tell you that these are the stories that will come about some particular transition metal dichalcogenides work that we've done. But let's see what polytypes are. And what you notice here are pictures of single crystals of these transition metal dichalcogenides. So I want to tell you why we care about single crystals and what single crystals are. As you probably are familiar with, they're periodic arrangement of atoms, where, for example, one of these bricks represents the periodicity of the crystalline lattice, and in a wall, you've built the wall with the bricks that are lined up parallel to each other. This is what we call a single crystal. And the properties of a single crystal are such that if you looked in any one direction, all of the unit cells are aligned in the same direction. But if you break this wall, so this is an example of a single crystal. If you break this wall, you still have that periodicity, but on a much smaller scale, and the different bricks are no longer aligned. So if you looked in any one direction, for the different bricks, you would see different orientations. And that's a polycrystal. So as you can probably imagine, the properties of polycrystals are different. I'm probably going to skip this because I have a lot more to say later. So one of the questions you may ask is, well, why do we care about single crystals? As you can imagine from the crystal structure and what I've just described, single crystals usually have fewer defects. And because they have fewer defects, typically that means better physical properties. If nothing else, think of transport. What would happen in transport, in electrical transport, in a single crystal versus polycrystal of the same compound? What do you think would happen?
It'll probably be better in a single crystal.
Probably be better in a single crystal. Exactly. Why is that the case? Exactly. There are fewer disruptions to the electron path, right? The electrons learn how to scatter off in a single crystal because they know the periodicity. Once you have a polycrystal, there are many more scattering events for a single crystal, which makes the resistivity larger. So in a metal, that would be bad, right? The metallicity would go down. And I have an example to show you exactly for that. I'm going to skip this. An example is titanium diselenide. Look at the resistivity here. The polycrystal resistivity is shown in the solid line over here. And you see that we are not going to talk right now about what this hump really means, but you can see that the resistivity is larger in the polycrystal than it is in the single crystal. And here I'm showing the single crystal measured with current in two different directions. One in the AB plane, which is the plane of this plate, and another with the current perpendicular to the plate. And so you see that both of these have resistivities much lower than the polycrystal, and that's exactly because of the different grains that occur in the polycrystal that are not there in the single. Sorry, I keep mixing it. All right, let's try to understand a little bit what I refer to as polytypes, so that you can appreciate the versatility of these transition metal dichalcogenides even at the structural level, and then perhaps that makes it easier to understand why they're so versatile in terms of their physical properties. So here's the transition metal lattice. Typically it's a hexagonal lattice like the one that I'm showing here, and now you're decorating that with the chalcogen atoms. Where do they go? Well, they usually form some type of coordination polyhedron around the transition metal. So let's see. In this case, the coordination polyhedron is, for example, an octahedron. All right? And now if we look from the side, we see this octahedral layer. And imagine that you have to stack these layers on top of each other. You can stack them perhaps one of two ways. Think of an egg carton. When you take an egg carton, you can stack them more efficiently if they sink into each other, right? Which means that the layers are parallel to each other, all right? But now, the other way you can stack the egg cartons is if you stagger them, or if you close the egg carton, that's the same as staggering them. But now you need two layers in the unit cell, as opposed to in the first case when you only needed one. So this is an example where the egg cartons are stacked most efficiently exactly on top of each other, which means that the unit cell, as shown here in the black outline, is formed only by one layer. And because of that, we call this the polytype, or that gives the 1 in the name of the polytype. And then the symmetry, the overall symmetry of that unit cell is trigonal, and so the name of this polytype is 1T. So if you've heard of transition metal dichalcogenides, you've heard of 1T, 2H, 3R, 4H, and then you've heard of 2HA, 2HB, 1T prime, etc. There's a lot of them, right? 4H, 6R. And well, the way they come about is because of this stacking and because of the coordination polyhedra that the chalcogens form around the transition metal. So here's another example where instead of the octahedron, you can have a prism, right? So now you have another possible transition metal dichalcogenide. If you looked at the AB plane, it looks exactly the same as the one I showed before. But now the coordination is this prismatic coordination, and this is what the layer looks like. So now you can stack the layers, again, either parallel on top of each other, or you can stagger them. And if you stagger, because you need 2 layers in the unit cell, the polytype is called 2H, and the H here stands for hexagonal because of the symmetry of this unit cell. You with me so far?
Yes.
All right. Good. And from here, we can imagine other ways of stacking, other ways of rotating relative to each other. Some of you may have heard of this type of stacking in the context of graphite or different layers of graphene stacked on top of each other that are rotated, right? So you have the ABC stacking. That's exactly the same that's happening here. So with this, I come back to the picture that I showed earlier with all of these polytypes. But now we all know what the polytypes are, right? Interrupt if you have questions. You have a question? No? Okay. But please stop me if you have questions. So now, hopefully, you can sort of make sense of what I'm showing you schematically here in terms of all these polytypes, right? So all of us are experts in polytypes now? Great. So I'm showing you some remarkable compounds in this family of compounds. Titanium diselenide only forms in the 1T polytype, while tantalum disulfide, notice that it's almost everywhere. So it forms in a lot of polytypes. All right? And therefore, the physical properties differ depending on what polytype you have. Yes?
Why the is hexagonal, but I think the 1T is also hexagonal.
I'm sorry?
Why the 2H is hexagonal? I think 1T is also hexagonal.
It's trigonal. It has some other symmetry operations compared to the H or the hexagonal polytype because of only 1 layer in the unit cell. We can look at the symmetry operations some other time.
So the hexagonal is the symmetry of the unit cell?
The polytype name refers to the symmetry of the unit cell, yes. Yes. All right. What are polytypes and what are polymorphs? Because some of you may know of polymorphs and now you've learned about polytypes. So how should you understand that? And in the context of the last few days, carbon is one example of the simplest material that will form in various polymorphs. And those polymorphs are graphite, the diamond structure, the buckyball, the carbon nanotubes. So what does that mean, polymorph versus polytype? The polymorphs are different crystal structures for the same composition of the material. So in this case, it's carbon. Polytype is a subset of that, and polytypes only differ in the way that the layers are stacked. Does that make sense? So they all have ultimately trigonal or hexagonal symmetry, but the difference is coming from the way the layers are stacked, and the layers themselves are identical in any one polytype. But in the carbon case or in other polymorphs, you see that in the hexagonal or in graphite, the carbons form a hexagonal or honeycomb lattice. In the diamond case, they form a cubic lattice, right? All right. Chocolate, if you didn't know, is also forms in several polytypes, and it has a molecule called theobromine, which is crystalline. So if you're interested in the crystallinity of chocolate, I can talk to you more about that. So I'll skip that because I want to get to the science of the transition metal dichalcogenides, but I'm happy to chat with any one of you that wants to later about chocolate. The one thing I'll say, eat your chocolate. If you leave it on the shelf, it decays from this tasty polymorph, known as polymorph 5, into this most stable polymorph, which is polymorph 6, where you start seeing some white stuff on top. Do you know what that is? The fat that separates. As the chocolate sits on the shelf, the fat and the cocoa or the theobromine separate, and that's the fat. So eat your chocolate, don't let it sit on the shelf, yeah? All right. Okay, so we talked about polymorphs versus polytypes. I remind you that the transition metal dichalcogenides are formed with these elements, and like I advertised earlier, they can be insulators, semiconductors, semimetals, etc. They have some things, some physical properties in common for almost all of the transition metal dichalcogenides. They almost all of them have something called a charge density wave, and almost all of them have superconductivity at very low temperatures. So what is a charge density wave? How many of you know what a charge density wave is? Some of you do. All right, well, good. Then I can tell the rest of you what a charge density wave is, and this maybe serves a refresher for those of you that know. So in a crystal structure, you have a periodic arrangement of atoms, right? Well, sometimes in particular materials, and we'll talk in a second about when and why, sometimes as you change the temperature, the atoms rearrange themselves into a new periodicity. So some of them come closer together, and naturally there will be a separation from the next pair. And when this happens, you have a new periodicity. And if you think of the charges in the lattice, there's a high density of charge where these atoms are closer together, right? And lower charge density in between. And this density of charge throughout space will look something like a wave, which is why we call this a charge density wave, right? So why does this occur in transition metal dichalcogenides, and why doesn't it happen in many other materials? What's one problem that you see with a charge density wave forming? Why doesn't the charge density wave always form? Why don't atoms always come closer together, or why do they respect this translational periodicity in the lattice? Because Coulomb repulsion says, no, I don't want two atoms to be too close together, right? They will space out in the lattice where they balance out all of the Coulomb repulsion between like ions, right? So in most cases, the most stable lattice is the one where we have this periodicity of the atoms that's the same throughout. Well then, how does a charge density wave come about? Well, there has to be some gain in energy when this happens that balances out the cost in Coulomb energy, right? That gain in energy comes from the fact that, you may know, when you introduce a new periodicity in the lattice, you're opening up a gap, right? So that's what happens over here. You had the blue band structure over here, but with the new periodicity, you're introducing a gap at the Brouwen zone. If the gap is large enough, what happens is that the energy of these electrons has dropped. So I've gained some energy by lowering the energy of those states. And if that gap is large enough and I've lowered the energy enough, I can compensate for the Coulomb repulsion. And if you looked at this plot over here at the top, we don't really have to concern ourselves with exactly what this represents. For whatever is worth, this is called a generalized susceptibility as a function of the wave vector Q. Notice that in 3 dimensions, this is continuous. In 2D, it has a discontinuity at the Fermi wave vector Kf. And then in 1D, it diverges. Well, nothing in nature likes to be this discontinuous or divergent, right? So when that happens, then it's more likely that something else has to take place to avoid that divergence, and that something else is exactly the charge density wave. So now if I ask you, why does charge density wave occur in transition metal dichalcogenides, which remember are layered materials? Why does it happen in TMDs and not in most other compounds? Because they're these 2D compounds, right? So they resolve this problem of the discontinuity in their susceptibility by going to a charged ST wave state. So in 1D and 2D materials, charged ST waves tend to be most stable. There are very few 3D materials where this happens. Right? And the charged ST wave was first discovered in a 1D material in niobium triselenide, and then it was observed in some materials called blue bronzes, which are some oxides that are very one-dimensional. Well, I think I have an example of something like that over here. So this is a nearly one-dimensional material, niobium triselenide, and then this is what the resistivity looks like. So it's metallic at high temperature, and then at some temperature, like 150 in this case, notice an increase in resistivity. Why does this happen? Remember that gap opening at the charged ST wave? So as the gap opens, there's a jump in resistivity. And there's some details over here. There's a second, or it's believed that there's a second charged ST wave. Let's not talk about that. Any questions about this so far? No? All right. Yes?
How do charged density waves differ from like a Mach insulating phase when you like form double bonds of sites?
Well, in a Mott insulator, you have your electrons are prevented from jumping from one side to the other, so they're prevented from moving throughout the lattice. That's different than the charged ST wave, which is a modulation of the lattice itself. So they're different physics. All right.
It's also often accompanied by a metal insulator transition.
Well, that's the metal insulator transition. You have a metallic state over here. It's not insulating, but it's a small gap opening up. And notice that the resistivity shows metallicity, or it becomes metallic again. It doesn't diverge. One of the reasons for that is because you're not gapping up the entire Fermi surface. You're gapping up just some Fermi surface. I haven't mentioned this, but you're gapping basically the part of the Fermi surface that's nested. So one of the mechanisms behind the formation of charged ST wave is the nesting, where you have parallel sheets of the Fermi surface that are translated by the same wave vector. So you're gapping the Fermi surface in that direction of the nesting wave vector. All right. Why does what?
Why the gap will increase the resistivity?
When you have a gap, the resistivity increases, no?
Yeah, why will it increase?
Why does it increase?
Yes.
Because a gap is associated with less metallic, more semiconductor or insulating behavior. I'm not sure what you're asking.
So you mean when you form some kind of gap, you will
When you have a gap, you no longer are in a metallic state, but a semiconducting or insulating state, right? In a charged ST wave, you don't open a gap big enough to be insulating, but you're semiconducting. So you're going from metal or semi-metal behavior at higher temperatures, and when you enter the charged ST wave state, you've opened up a gap, so your resistivity is increasing. It's larger because of that gap. You don't have states at the Fermi surface anymore.
But if you have a gap and you form some kind of insulator, but your resistivity is also smaller than the metallic phase.
I just said that you're not gapping the entire Fermi surface. You're just gapping the parts that are nested. And therefore, as you're lowering the temperature enough, you're recovering the metallic behavior. That's what's happening in this particular case. And that's what's happening in titanium diselenide, for example. And in some TMDs, you will see the resistivity go up. So if you're gapping more of the Fermi surface, then the resistivity increases more. All right. Good. Well, let's come and talk about what happens if you now take these TMDs, which are already very diverse in terms of their properties, and you try to do something chemically with them to enrich their properties even further. Some of the things that you can do is doping, which you know you can do in almost all materials, right? When you can substitute some of the constituent elements with others, and then because of the dopant, you may bring about different carriers, or you can bring about some different magnetic properties. In the TMDs, we can do something even more than doping, where we can intercalate. And the difference between doping and intercalation is that instead of substituting for atoms that exist in these layers, we can intercalate in between the layers. And I haven't mentioned that the layers in TMDs are weakly coupled by something called van der Waals forces. And if we can place an atom in a van der Waals gap, then we can bring about more properties or different properties to the transition metal dichalcogenides. And you can imagine that you can push the layers further apart or bring them closer together. You can see magnetism, superconductivity, etc. So let's see how much I can tell you about some of these materials that we've worked in my group. But if we don't get through all of this, and my goal today is not to rush through everything, but rather to have a discussion like we've already had. But if you don't remember anything, you should remember that in doped or intercalated TMDs, you can have magnetism, often unconventional magnetism. You can have superconductivity, like the example shown here. You can have a metal to insulator transition, which is another example that I hope to get to tell you about. Or you can have superconductivity and something called unconventional topology or unconventional topological fermions or Kramer's nodal lines. Or you can have both or a combination of different things. All right. So let's see. Let's go through these and see how much we get to cover in the time that I have left. I think I have about half an hour, 30 minutes. All right. So let's talk about unconventional magnetism in a particular class of TMDs. These are iron intercalated tantalum disulfide compounds. So this form in a 2H polytype. So you have the 2H tantalum disulfide, and when you put iron in the van der Waals gaps, the compound stays 2H, still retains this polytype structure. But now what you notice in this electron diffraction is that in addition to the very bright spots, which correspond to the underlying tantalum disulfide structure, you have spots halfway in between each of these. So it means that you now have a superstructure, which is a 2x2 superstructure. The way you should know that it's 2x2 is that you have these bright spots in both the A direction and in the B direction. So the unit cell, the electron diffraction here is a representation in reciprocal space. So because we have spots halfway between the primary spots, what that means is that the real space unit cell is doubled in the two directions, right? So that's the 2x2 superstructure that we have here. So instead of the modulation that I showed here in an example of a one-dimensional chain, now we have a modulation in 2D. And that happens in a particular case of iron, for iron a quarter. So when X is equal to 0.25 or 1/4. And when that happens, if we measure the magnetization versus field, that's the blue curve over here, notice that it looks like there's very sharp switching at some field close to 3 Tesla. And then if we measure the resistivity as a function of field, that's plotted in red, the same sharp jump occurs at the comparable field. Well, how should you interpret that? Well, this is what you would expect for a hysteresis loop, right? The normal hysteresis loop should look more S-shaped than what I'm showing you in the previous slide. Well, why does that happen? Well, we're trying to understand that by looking at the temperature dependence of these magnetization isotherms and of the resistivity isotherms. So it turns out that in this ordered superstructure, 2x2 superstructure, the moments are parallel to the C direction, so they're perpendicular to the plate or to the planes, and they all switch at the same time, giving rise to this very sharp switching. And when we now look at the magnetoresistance as a function of temperature, the black curve over here was the lowest temperature. Before I showed you actually an even lower temperature. What was that? It was, I didn't write it over here, I'm sorry. It's 2 Kelvin. But even as we go to higher and higher temperatures, the magnetoresistance has these bow tie shape and the very sharp switching. Up to about 100 Kelvin. What I didn't tell you is that the ordering temperature in this compound is 160 Kelvin. So even to temperatures far in excess of the half or of very large temperatures, even compared to the ordering temperature, the resistivity retains this bow tie shape and the very sharp jump. However, overall, notice that the jump in magnetoresistance is only about 1%. So the way we characterize magnetoresistance is by plotting it like delta rho over rho naught. Well, delta rho is the resistivity at some field value minus the resistivity in zero field, scaled by the resistivity in zero field. So that gives us a percentage. And in this case, notice that the magnetoresistance is about 1%, nothing to write home about. In metals, that's what you would expect. The exceptions which you may be familiar with are systems which show colossal magnetoresistance or giant magnetoresistance. And those are typically based either on some complex heterostructures or manganese-based compounds. So in those cases, you may expect very large magnetoresistance, but in normal metals, you wouldn't. However, if we change the iron content, so now we're going away from 0.25 from that 2x2 superstructure to something close to 0.3, but not exactly 0.3, and not a superstructure anymore, then the magnetoresistance increases by a couple of orders of magnitude. And if we think of what we discussed earlier about disorder and such, in the 0.3 or 0.297 composition, the irons are no longer ordered in the layer, and therefore there's more disorder, which naturally gives rise to more scattering, high resistivity, and therefore this is behind this increase in magnetoresistance. And here's a summary of the MHs in the series of iron tantalum disulfide with different compositions, where starting at about 0.23, notice that the hysteresis loops look exactly like you expected, more S-shaped like, but as soon as you get close to 0.24 or so, you start seeing this sharp switching. And notice that the fields at which the switching happens can be very large, more than 7 Tesla in this case, and then 3 or 4 or 6 Tesla in this case, etc. And as a function of the composition, there's great variability in these properties, and that's reflected also in the transport. And this is the summary of the magnetoresistance for the exact same compositions. Yes?
I'm just curious, does the van der Waals attraction affect the magnetism?
Does it affect the magnetism? Well, you're putting irons in those gaps, so I think once you've populated the sites over there, the layers tend to be more coupled to each other. And so the crystal structure still remains 2D, but electronically the materials may no longer be 2D, two-dimensional, and the van der Waals gaps are no longer relevant. The charge density wave is gone when you put in magnetism, but I'll show you an example soon where even though you start putting stuff in the van der Waals gaps, the charge density wave doesn't disappear right away. So the compounds retain their two-dimensional or lower dimensionality even when you intercalate them in some cases, and that's why you may still see a charge density wave. But now you start to add things in the van der Waals gaps, so I couldn't tell you how relevant the van der Waals gaps are at that point, right? Yeah?
So to what extent can you think of these materials as like a 2D layer with like a 1D lattice in a third direction of, I don't know, iron? Or do you really have to consider the interplay between the iron and the layer?
Yes, the coupling of the... Everybody heard the question? The irons in the layer are much closer to each other than they are to the irons in the next layer. And so the lattice parameter tends to be larger in the C direction than in plane. And so the coupling is stronger if the distance is smaller. Therefore, the coupling in the plane is the most relevant. All right, so if you've been staring at this is a summary of the various properties of the materials I just showed you, iron tantalum disulfide as a function of composition, where we have the ordering temperature, the switching field, that sharp switching field, the magnetoresistance, etc. So if nothing else, what you can take from this is the fact that there seems like there's a singularity in all of these properties at the superstructure, and there's supposed to be another superstructure at the 1/3 composition. We have not been able to synthesize it yet. I don't know if anybody that has made it in single crystal form. In polycrystalline form, yes, we have seen that. But in any event, so you see how the physical properties don't change monotonously as a function of composition. And to me, the most striking is the fact that the ordering temperature varies so much. So in x equal a quarter, the ordering temperature is 160. On the sides, it's down to 40 or less. According to what I just said, that if the distance is smaller, the coupling should be stronger, the temperature should be higher for higher compositions, and yet that's not the case. So that's still something that we don't understand, we're pondering on. All right, let me switch now and talk about superconductivity, and this is going to be indeed an example where even though we intercalate copper in between the layers of titanium diselenide, the charge density wave still persists up to some composition, and even after we've now started seeing superconductivity. So let me tell you this story now, which has to do with 1T TiSe2. So it's a 1T polytype where the seleniums form an octahedral octahedron around the titanium, so they're octahedrally coordinated. And copper goes, like I said, in the gap in between the layers. Titanium diselenide is one of the very few TMDs which does not show superconductivity without pressure and without chemical doping or intercalation. So then it was surprising, and it was one of the first examples of inducing superconductivity chemically once we intercalated copper. So when copper is intercalated, here I'm showing the susceptibility starting with that of the pure TiSe2 in black, and the other curves correspond to increasing amounts of copper. We haven't talked about what the susceptibility should show if you have a charge density wave. But remember the gap that occurs in compound at the charge density wave transition, where the susceptibility of non-magnetic compounds is proportional to zeroth order to the density of states at the Fermi level. All right? So when you're in the metallic state at high temperatures, you have one susceptibility. What should happen to this susceptibility if now you open up a gap and therefore you lower the density of states at the Fermi level? The susceptibility should decrease, right? And that's what we're seeing here. We're seeing a step down in susceptibility at the charge density wave. And what you notice is that as x, the amount of copper, increases, the CDW goes down. And now, in this plot, I'm not showing the low temperature susceptibility for many of these compositions, but what I'm showing on the right here is the resistivity as a function of temperature for the same compositions. And notice a drop starting at about 0.4. Maybe you can't see it very well in 0.4, but for higher compositions, you notice there's a drop. And if we now look closer, the resistivity shows a drop to 0 for some of these compositions. The susceptibility also shows the signature of superconducting transition with a drop from at the TC. What you should notice is that the superconducting transition, which occurs at about 4% copper in the green curve over here, this superconducting transition moves up in composition until about 8%, and then at 10%, it changes its mind and goes back. And that's reflected on this phase diagram. And you see here a summary of the charge density wave and the superconductivity. But notice that the superconductivity occurs at very low temperatures, below 4 Kelvin or so. So this phase diagram, for those of you that are familiar with the high temperature superconductors, is very much reminiscent of that in the cuprates, minus the fact that the temperature is nowhere near the high values in the cuprates, right? And for what we understand now, the mechanism is also very different. But it's a striking change of both the charge density wave and the superconductivity with intercalation. And to your question, the charge density wave still persists even when we have some atoms in the van der Waals gaps, right? It only goes away at about 6%, maybe if we extrapolate this, I suspect that it goes away close to the peak of this dome. So perhaps there's some correlation between where the charge density wave disappears and where the temperature is maximum. That's not something that I understand at the moment. So when I worked on this material, one of the questions that came about was, well, why does copper do this? And do other elements, do other intercalants have the same effect? One of the things that my postdoc supervisor, one of his mantras was, if it doesn't have copper, put it in. He was a high temperature guy, so he was well known for work on the cuprates. So his slogan was, if it doesn't have copper, put it in. If it does, take it out. So I tried to put copper in all sorts of other transition metal dichalcogenides. As of all of those that I've worked on, putting copper or other elements, only these showed superconductivity. Another example is copper tantalum disulfide. So yes, if it doesn't have copper, put it in, it seems to work. Well, not only that, but palladium seems to work. And by looking at these phase diagrams, you can see that there's some similarities and some differences. For example, tantalum disulfide does superconduct even without intercalation, but with copper, it tends to go up and forms this dome-like shape, much like what happened in copper TiSC2. And then, yes, the CDW again comes down and disappears before the superconductivity goes away. However, in the palladium case, it looks like the charge density wave disappears, and only then do we see superconductivity for a very limited composition range. All right. Yes?
Why in the copper case do we see a kind of like a fading out of your metal CDW transition compared to a sharp distinction?
Oh, I can't measure it anymore. It's not that it's fading, but if you think about it, my measurements are all at fixed composition. So I'm measuring as a function of something, temperature, for example, right? So when this line becomes too vertical, then as I'm measuring this way, I can't see it. That's the only thing.
So
Yeah.
it's an actual phase transition?
I'm sorry?
It's an actual phase?
It's an actual phase transition, yes. And the dotted line and the dotted symbol there is because I still have a hint of it in some measurements, but it's not very clear. And it's because the phase boundary now becomes very vertical. So when you have a phase boundary that comes like this and you're trying to measure along that direction, you usually don't see much of a change in your thermodynamic or transport properties.
Have you tried looking at it optically? There's charge density wave, you can usually see a phonon appear.
I'm sure there's been many studies. This is 2006, so I'm sure there's been many studies that have looked at it. Yeah. And people have started looking at just pure TiSC2 after this discovery because now everybody wanted titanium diselenide is very rich itself in its properties, and a lot of work was dedicated to understanding its properties now that it showed this superconductivity. So, yeah.
In the figure on the right here, there are these two charge density wave regimes. Can you explain kind of the emergence of that second phase?
I can't. I see it in my measurements. I haven't shown you any data on that, right? So I see it in my measurements and notice that that's a very generous phase there. I have a point. Again, because if I wanted to measure it, I would have to cut the boundaries perpendicular or close to perpendicular. There's no way to measure as a continuous as a function of composition, right? So I only see it in one composition, which tells me that there's a very narrow phase that has it. I don't know a lot of the details of what kind of charge density wave that is. But a lot of materials like the niobium triselenide that I showed you can have multiple CDWs, right? So, and again, the superconducting dome in this case only has also only 2 points, right? So, but one thing that I will tell you next is that as a detour from the main story is trying to understand why does superconductivity show up in some of these compounds and why do others show, for example, insulating behavior. For example, if you looked at this plot here, so let me walk you through it. If you put, here's the periodic table. You have copper, nickel, palladium, platinum. So if you put copper in, the resistivity right away becomes more metallic, so it starts going down as a function of temperature, and eventually it shows superconductivity, right? This is TiSC2 over here, the black curve. So you see that the copper, overall the resistivity is lower, so this material is already more metallic. If you put nickel in, nickel tends to make it slightly less metallic or slightly more semiconducting if you want. Put palladium in, palladium, remember I said that it superconducts eventually. Before it goes superconducting, the resistivity actually goes up by 2 or 3 orders of magnitude. And only for enough palladium will it come back down, become more metallic and superconducting. Put platinum in, so we go from nickel, copper and nickel to palladium and now to platinum. Put platinum in, this goes up, almost blows up. It goes up by 7 or 8 orders of magnitude. And as far as I can tell, it never comes back down to become superconducting. So Aparna, the student in my lab, who is an NRT student, is actually now working to try to understand what's the origin of this behavior that goes more and more insulating as I move down in the periodic table. One thing that changes as you go to heavier and heavier elements is the spin-orbit coupling. So we're trying to measure the spin-orbit coupling and see if that has something to do with this metal or semi-metal to insulator transition that happens as a function of the different elements. All right. All right. Ready for another story? That's the platinum TiSC2, which I alluded to just now. And here's the resistivity, which is insulating. In this case, unlike what I've told you so far about the different elements intercalating in the van der Waals gap, it turns out that platinum does not intercalate, but rather substitutes for titanium. And one way we know that, we've done some neutron diffraction measurements that have confirmed it, but what suggested that as a possibility is if we looked at the lattice parameters. The lattice parameters, as a function of platinum, didn't really change. All right? In the case of intercalation, you see a linear change in the lattice parameters, both A and C. In this case, there wasn't any change or not any substantive change or systematic change, and that told us that maybe we're not intercalating but doping, and eventually we did confirm that. So stay tuned until we find out why we go from a metal to an insulator as we come down in the periodic table. The last bit that I want to leave you with is a story of topology that occurs in transition metal dichalcogenides. And we may not talk in detail about what kind of topological properties these are, but I want you to just understand and appreciate that depending on what you intercalate in which transition metal dichalcogenide, you can have different properties. So here's, I don't know how much we should talk about Kramer's nodal lines and Kramer's Weyl fermions. This is some work that we've done together with Professor Ming Yi. These Kramer's Weyl fermions are some new fermions that at the time when we started working on them, they had been predicted theoretically. And they're these fermions which have a property where they are they show degeneracy in the reciprocal space at some high symmetry points called time reversal invariant momenta. There's these pinch points here in this particular band structure. And then the bands are split or non-degenerate away from those trims. And this happens in chiral crystal structures. If we have achiral crystal structures, apparently something else happens where instead of having degeneracy just at single points, at trims, you now have degeneracy in a line between trims. So look at this. This is a band structure without spin-orbit coupling. And pay attention to, well, if you can see it on this screen, pay attention to the blue lines over there. Notice how the blue lines still remain degenerate, but away from those blue lines, the bands are split. So I'll do this one more time so that you can follow. So between Z and gamma over here, the lines are degenerate right now and they're degenerate away from it. But as we introduce spin orbit coupling, those lines between Z and gamma stay degenerate and they split when we go away. All right, so this is as much as I'm going to tell you now about Kramer's nodal lines. The first compound where we found these Kramer's nodal lines, the ones that had been predicted theoretically, was samarium aluminum silicon. But more recently, we worked on indium intercalated tantalum disulfide. So remember the iron earlier? It was the story of tantalum disulfide. We put iron in it, it was magnetic, fun things happened. When we put indium in it, totally different physics. So take a look at this here. So what I'm showing you is that depending on how much indium we put in, we can have, probably I should stick to this, depending on how much indium we put in, so if X equals to 1, the indiums go directly on top of sulfur, so that's one crystal structure. If we put X equal 1/2, or we manage to actually grow some crystals with a composition of 2/3, the indiums go directly on top of tantalum. Both crystal structures are achiral, and I told you earlier that in an achiral crystal structure, you expect to see Kramer's nodal lines. So we want to see something where the bands are degenerate for the line between two trim points, and then they split away from that, right? So that's what Ming and her students did. So this is ARPAS data from her group, and that's exactly what you see here. You see the splitting the bands away from these trim points. So this confirms the Kramer's nodal line in this intercalated TMD. But more than that, when we measure the transport of those three compositions, one thing that you notice they have in common is the superconducting transition that occurs at different temperatures. And in some case, like X equal 1, the transition is very sharp and it occurs at somewhere around 0.9 Kelvin. And it's not so nice and much broader in X 1/2 and even more broad in X equal 2/3. But notice that the transition happens somewhere around 2.5 or just below in this composition, or at 0.5 or so for X equal 1/2. Very big differences in TC, in the transport as a function of temperature. So, the last thing that I'll mention is this composition also has a charge density wave. The other ones don't anymore. So the charge density wave completely disappeared in X equal 1 and X equal 2/3 with this indium intercalation, but it seems to survive in X equal 1/2. So